All right, here we go. Today is going to be a lot of definitions, so there won't be a whole lot of problem solving today. For the most part, we're going to just sort of give ourselves a baseline of here's what things mean when we say them. And that's a real important thing mathematically, is we can't really use a term until we have defined the term. Now, some of them I know you're very comfortable with, and it may feel like, really, you're giving us a definition for that? But I want to make sure we're all talking in the same language when we talk about these objects. So we're going to start out with points, lines, and planes. And the first thing is, well, a point is just, a location in space. Generally, we're talking about, at least for right now, a two-dimensional space, like, on a piece of paper is a great two-dimensional space. It has length and width. Technically, it would have a height, but we can kind of ignore that and say that a piece of paper is a two-dimensional space, and we could put a dot on there, and that point is just a location in space. And this question is, how many lines can go through one point? And you don't have to have the right answer here, but I'm just curious what you think. How many lines could I draw that go through that point right there? And don't overthink it. Your instinct is correct. Great, Sunshine. You're exactly infinitely many. Well, I could draw this line through there, and I could draw this line through there, and I could draw that line through there, and I could keep going. I could keep drawing lines that go through that point. Infinitely many. So I can draw an infinite number of lines through any one point. All right, well, let's see if we can tighten this up a little bit. How many lines can go through 2 points? So now if I have 2 points, how many lines can I draw that go through both of those? It has to go through both of them. How many could I draw that go through both of those? And geometry may be something that's a little rusty for you. One thing I want to say is, if you're thinking back to high school geometry and you're concerned about those 2-column proofs that you did, where you'd say, AB is equal to CD because of the reflexive property, or, the angle side angle, or any of those we're not going to do that kind of geometry. We're going to talk more big picture sort of definitions and how things work. As far as these two lines go, these 2 points go, there's only one line I can draw that goes through those 2 points. That's it. There is no other line I could draw that goes through those 2 points. So when I have 1 point, I can draw infinitely many lines through it. If I have 2 points, there's only one line that can go through those 2 points. What this tells us is that 2 points determine a line. Because there's only one line I could draw that goes through those 2 points. All right, let's keep moving along here with the same idea. What if I have 3 points? Well, now this one, I'll answer for you. This one depends. It depends on how those 3 points are arranged. If those 3 points happen to be arranged like this, then I could draw one line that goes through those 3 points. I could draw one line that goes through the 3 points, and it would look like that. If this happens, we would say that those points are, and this is another definition for us, collinear. Now make sure I spell that correctly. There we go. We would say that those points are collinear because they're on the same line. They're collinear. If instead my 3 points are not arranged so that they would create one straight line. How many lines could go through those points? Well, if I try to draw a line here, well, it doesn't hit the third point. And I could draw a line here and it doesn't hit the third point. And I could draw a line here and it doesn't hit the third point. So there is no line I could draw that goes through those points. You know, like I said, I could draw this one that only hits 2. I could draw this one that only hits 2. I could draw this one that only hits 2. We would say that those points then are non-collinear because there isn't one line that I could draw that would go through all 3 of them. And so it kind of depends on how they are arranged. And that's the terms collinear and non-collinear. Collinear means they're on the same line. Non-collinear means I can't draw a line that goes through all 3 of those points. Let me know if you have questions on that before we go forward. Okay. So we've talked about points, we've talked about lines. Now let's talk about planes. I can tell you we're not going to spend a whole lot of time talking about planes, but what a plane is it's a 2-dimensional space. So a plane is a 2-dimensional space. You could think like the top of your table as a 2-dimensional space. Or if you wanted to, you could pick up a piece of paper and just sort of ignore the fact that it has any depth to it at all. And if you have a piece of paper, just length and width, that would be a plane. And what we see over here in this image on the right is, you know, there's this light blue plane here. And then I could take my piece of paper and I'm holding it straight up and down to be the light blue one. I could rotate the top away from me a little bit. And that would be the white plane that's here. And then I could rotate it even further till not quite horizontal, but getting there. And that would be the gray plane that's here. And what we're finding here is in the same way that a point can have an infinite number of lines that go through it, if we have 2 points, then connecting those 2 points, an infinite number of planes can go through there. And that's kind of, if you think about the 2 points here, if you were to hold a piece of paper and do exactly what I was kind of describing there, where I'm holding it vertically and that's the blue plane, and I've kind of got it pinched between my index finger and my thumb on the left and my index finger and my thumb on the right. And then I rotate it a little to get the white plane and I rotate it a little more to get the gray plane. You can kind of look at where your index finger and thumb come together. That's these 2 points. And those 2 points define an infinite number of planes. So I have 2 points. I have an infinite number of planes that could go through them because I can rotate my plane just a little bit further each time to get an infinite number of them that would pass through those 2 points. Now we're going to get to 3 points. And our assertion here is going to be that 3 non-collinear points define one single individual plane. Just to sort of back up for a minute, 3 collinear points define one line in the same way that 2 points define one line. What we're saying now is 3 non-collinear points define a plane. When I had 2 points a couple minutes ago, when I only had these 2 points, I could get an infinite number of planes that go through there. But if instead of that, now I get to where, you know what? Instead of having 2 points, we're going to have 3 points. That defines a plane. There's only one plane that can go through all 3 of those points. If I think about my piece of paper and I needed to go through all 3 of those points, sure, I could use these 2 and I could rotate back and forth, but I only get a plane that goes through all 3 points when this point up here at the top is included also. So 3 non-collinear points define a plane. And the best way to imagine this, the best way to show this to a kid, if you happen to be studying points, lines, and planes and you want to keep it very visual for a student, is if you just think of a stool that has 3 legs. When a stool has 3 legs and you put it on the floor, those three legs touch the floor at one point, that's the plane. That's it. If you take away one of the legs, now you could have, your stool could rotate back and forth. But once you have that third leg and you need all 3 points to touch, it's going to touch the floor, and that floor is the plane that three-legged stool defines. Those are 3 non-collinear points. The three-legged stool touches the floor in a way that defines a plane. A really nice thing to tag along to this is the idea that if you have a stool with 4 legs, like I do in my house, and boy, they never seem to touch the floor perfectly. One of them's always a little bit off. It can wobble a little bit. That's because the 4-legged stool doesn't, now we don't define a single plane. We're rocking back and forth. But a 3-legged stool will never wobble because that 3-legged stool defines a plane. And so it's a perfect example of that. We won't spend a ton of time on planes. I want you to understand that a plane has length and width. Think of it as a piece of paper and imagine that they're, or the top of a table. The top of a table is perfect. That's a plane. And a 3-legged stool won't wobble because those 3 points define that plane. All right, now to something that's a little more familiar, probably. We're going to talk about lines, line segments, and rays. A line, we've already discussed a line a little bit. A line goes through, it can go through more than 2, but if we have 2 points, that defines a line. And a key thing about a line is that it goes on forever in both directions. So for a line, we need those arrows to indicate that it goes on forever in both directions. If we want to name a line, then we're going to need to know the names of points that are on that line. And so here, what we could call this is, we could call this line AB, and that's how we would abbreviate line AB. We'd use a symbol that looks kind of like a line, and then we would have AB under there because those indicate the points that it goes through. Lines go both directions. They go forever in both directions. So we could also call this line BA. It would mean the exact same thing. It's a line that goes on forever in both directions, and it goes through the points A and B. As we go through these sort of terms, definitions, symbols, way to write things, let me know if anything comes up that you have questions about. I want to make sure we're all clear on how we're going to describe all of the things that we'll be discussing. Okay, line segment. A line segment is just a piece of a line. It has a start and a stop point, and those might be A and B. But instead of going on in both directions forever, this has a start and a stop. And the way we're going to describe this is with AB with a line with no arrows. That's how we know it's a line segment. It doesn't go on forever. This goes from A to B, stops, and that's it. Now this goes both directions. So if we wanted to call it line segment BA, that's totally fine. That's the exact same line segment that we have with line segment AB. It goes from A to B, or it goes from B to A. Either way, that's that line segment. I want you to think of a line segment as just being a subset of a line, because that's exactly what it is. Line AB over here goes on forever in both directions. Line segment AB, that's just a piece that goes from A to B and stops. That's it. So it's a subset of a line. Finally, we have a ray, and a ray has a starting point, goes through a point, and goes on forever in one direction. So this could be, say, ray AB, goes on forever in one direction. This one, we could call it ray AB, probably uses the notation that you would expect. The arrow goes in one direction. This one's a little different from the others. I can't call this one ray BA. That's no good here. And the reason is because this ray starts at A, goes towards B, and that's the direction it goes forever. I don't want to call it ray BA because that's not what happens here. It doesn't start at B and go towards A. That doesn't happen, so we can't name it both ways. We can only name a ray in the direction that it's actually going. Any questions about any of those? Awesome. Different types of lines. We're going to talk about parallel lines, perpendicular lines, and concurrent lines. Parallel and perpendicular are probably pretty familiar for you. Concurrent may not be. That's okay. We'll clear it up. Parallel lines are exactly what you would think they would be. They are two lines that never intersect. Two lines that never intersect. They're parallel. I'm going to add one condition to this because of a definition that we still have coming up ahead of us later on. I'm going to say that they never intersect and they're in the same plane. We're going to get to a definition that's going to be, might be a new one for you, that where we wouldn't necessarily need this condition, but now we do. So parallel lines never intersect and they're in the same plane. Perpendicular lines. Perpendicular lines intersect, and they intersect in a special way. How do perpendicular lines intersect? One of you can tell me. I'll just kind of keep you with a little bit of back and forth here. There's so many definitions today that it's so much me and not much of you. Perfect, sunshine. They intersect at a right angle. This angle in there is going to be a 90-degree angle. So they're going to intersect at a 90-degree angle or a right angle. Those are perpendicular lines. And then finally, concurrent lines. Concurrent lines happen when we have three or more that intersect at a single point. So we have a single point and we have at least three that intersect in a single point. That's concurrent. And that may be a new definition for you, or one that you might have heard one time a long time ago and then kind of filed it away. It's not one we use very much, but it is one that comes up in our book, and I want to make sure you're familiar with it. So we could say that these lines intersect, and we could say they're perpendicular, but they're not concurrent because there's only two of them. Over here, since three or more intersect, those are concurrent. Are there any questions about those three definitions? All right. Here's that definition that I mentioned that might be new for you, why we had to say that parallel lines are in the same plane. Because there's another thing that we don't use often, but skew lines. They don't intersect, but we don't call them parallel. The reason they don't intersect is because they're in different planes. And I want you to kind of look at this picture right here with me for a minute. Before we get into skew lines, I just want to describe how, like, we can see that, you know, line segment DC and line segment GH there, if we made those lines that went on forever, DC and GH, those are in the same plane. The plane that they're both in is this plane right here. They're both in it. And that's why we would say that those two lines are parallel. They're in the same plane. They don't intersect. The piece of paper that we could write them on is this piece of paper. Oops, I erased. Is this piece of paper right here. We could have DC. We could have GH. They're in the same plane. They never intersect. So we call them parallel. In contrast to that, a little different from that. Oh, I got a little bit more erased too. There we go. A little bit different from that is if we look at line AD and line EF. We can see AD is up here at the top of the box and goes on forever. EF is down here in this bottom left corner of the box. And imagining that these are actually on a box, they are never going to intersect. They're never going to cross with each other. But it's not because they're parallel. It's because they're not in the same plane. AD is in this, AD is in this plane here. That's the piece of paper that's the front of the box. And then when we look at EF, that's on this piece of paper here that's on the side of the box. And so the reason they don't intersect is because they're in different planes. When that happens, we don't say they're parallel. We say these lines are skew lines. The reason they don't intersect is because they're not in the same plane. Not going to be a huge focus for us, but I do want you to know what skew lines are. And, you know, if you see the term skew lines, that you know what it's referring to. Two lines that don't intersect, but they're also not parallel. The reason they don't intersect is they're in different planes. If there's any question about that, let me know, because it is a strange one. Okay, fantastic. Angles. Angles are a union of two rays and have a common endpoint. It's a very formal way to write that definition, but it's a union of two rays. All right, so I have two rays and they come together. And so this angle is a union. That's joined together, just like it meant all the way back in set theory in Math 122. Union means joined together. So we take these two rays and we give them a common endpoint right here that we call the vertex of the angle. And that's an angle. Now I do want to talk about how we're going to name angles. We may have a point up here. Let's say it's point A, and B is here, and C is here. The way that we would name this angle is from one of the points out on the rays, then to the vertex, and then to another point on a ray. So we could name this angle ABC. And the reason we would name it like that is because what we're doing when we name this is, if you were to start at A, move to B, and then move to C. Start at A, move to B, and then move to C, you've created the angle that we're talking about. And so that's angle ABC. You could absolutely call it angle CBA, because that would be the exact same angle. We start at C, go towards B, go from B up to A, we've created the same angle, so we're talking about the exact same thing. Either of these is a perfectly okay way to name the angle. And it doesn't have to be in alphabetical order. We could certainly have an angle where the letters are X, W, K, and we just call that angle XWK, or we could also call it angle KWX. I suppose that bottom one there is in alphabetical order, but that's just coincidence. There's no magic to alphabetical order. There's no magic to where the vertices go. It's just what's really important is when you name an angle, the vertex is always going to be the one that's in the middle, because we're going from a point on a ray to the vertex to a point on the other ray. Any questions about any of that? Okay. Types of angles. We've got some specific types of angles that we want to take a look at. One of them we've kind of already seen, because we saw two angles that intersected at 90 degrees, and that's a right angle. A right angle is a 90-degree angle, and so it's going to look like that. We can put a little square in there to indicate that it's a right angle. That's usually very helpful for whoever is viewing the diagram. That's what that little square would mean, that we have a right angle, which means it measures 90 degrees. A straight angle is just, it doesn't really look like an angle at all. Where the angle is that we're talking about would be if we were to put a vertex here in the middle. It's this angle right here, and it's a 180-degree angle. So not a very interesting angle, but you can have a 180-degree angle, and there's what one looks like. We can have an acute angle. Anybody remember what an acute angle is? I'll give you a chance to chime in since you haven't had much of a chance to say much today. Sunshine's got us covered. That's awesome. Less than 90 degrees. So an acute angle is any angle like this one that is less than 90 degrees. So when we measure it, it's less than 90 degrees. That's an acute angle. And then finally, the last one that we'll talk about is an obtuse angle, which you probably guessed. We have less than 90, we have 90. What we don't have yet is obtuse, which is more than 90 degrees. And so this angle here is obtuse because it measures more than 90 degrees. Any questions about those types of angles? So that if I say a straight angle, you know what I mean. If I say an acute angle, you know what I mean. That's the main thing here. And that if you see these terms in your book or in homework problems, that you know what they're referring to. Okay. Adjacent angles. I've got two definitions written down here for adjacent angles. One of them is sort of the formal definition, and the other is a more informal way for us to just talk about them with each other. Adjacent angles have the same vertex. They share a common side, but the interiors are disjoint. Wow, that's pretty hard to wade through. Same vertex, share a side, but the interiors are disjoint. That means the interiors don't overlap each other. They don't have anything in common. Informally, which is probably how we'll talk about this, they're next to each other. And so an example of adjacent angles in this particular triangle would be angle CBD right here. And adjacent to that is angle DBE right here. Those two angles are adjacent. Angle CBD is adjacent to angle DBE. Hopefully, the way that I named those is comfortable for you. CBD and then DBE names the angles. If you have any question on how I named them, please let me know. And we can kind of see by looking, okay, so you've got this angle right here, and then right next to it, you've got this angle right here. Okay, they're next to each other. We can take a quick look at that formal definition just because I don't want you to run away from those kinds of things. They have the same vertex. Sure enough, I can see from how they're named or from the picture that B is the vertex of both of them. They share a common side. Yeah, this line segment BD right here, that's in both of those angles. And then the interiors are disjoint. And what that means is, well, the interior of CBD is totally separate from the interior of BDE, or excuse me, DBE. So that's what adjacent angles are. So when we talk about adjacent, that's what we mean. A couple of other words I want to take advantage of this picture to discuss. When we look at how, would you agree, even though my picture doesn't have a little square right here, if you disagree, tell me that angle CBE is a 90-degree angle. If you disagree, let me know. I didn't put that in there, but we can kind of see how it would be. And so what this tells us then is when I look at this picture and I see, okay, well, that means if I take angle CBD plus angle DBE, if I add those two together, angle CBD plus angle DBE, I'm going to get 90 degrees. If I add those two angles together, I get 90 degrees. Let me know if anything doesn't make sense or you're not sure of it. What that means, when two angles add to make 90 degrees, we say those two angles are complementary. Those are complementary angles if they add to 90 degrees. Similar to this, but a little bit different is, and I gotta figure out what I can scribble with over there that'll work out. Okay, similar to this and a little bit different is if I look at, let's say angle ABD, which I haven't looked at yet, but there it is. It's that obtuse angle right there. if I take angle ABD and I add that to DBE, let's see what happens there. So if I add those two together, so I'm taking this one, which is all of this, and adding it to this one, which is this right here. Oh, well, then those add to make 180 degrees. Two angles add to 180 degrees, we call them supplementary angles. A couple of the key takeaways from this page are adjacent angles are next to each other. We could say ABD and DBE, they're adjacent. Even though one's obtuse and one's acute, they're adjacent. Also, if two angles add to 90 degrees, we call them complementary. If two angles add to 180 degrees, we call them supplementary. Let me know if you have any questions on that. All right, doing great. Vertical angles. This is going to be useful for us later on when we're finding angle measures, but what vertical angles are is they're back to back. And here's what I mean by that. We might have a diagram that has a picture like that in it. And we could put vertices on here to name these angles, but there's another way to name angles that I want to make sure you see. Sometimes we just give them a number and we'll say that this is angle 1, angle 2, angle 3, angle 4. So we don't know any of the vertices here at all. We're not going to call them angle ABC or angle DBE or any of that stuff. We're just calling this over here angle 1. We're calling this up here angle 2, and so on. So that's another way we can name angles if we want to. It's just by throwing a number right in there in the part of the diagram that is the interior of that angle. And what happens when I have vertical angles is they are going to be congruent, which means they are equal. Their measure is equal. If one of them's 38 degrees, then so is the other one. And when I say back to back, what I'm talking about here is angle 2 and angle 4 would be equal to each other because they are vertical angles. Formally, what we would say about vertical angles is they share a vertex, but nothing else. That's what makes them vertical angles. They don't share any sides, but they do share a vertex. And then if we look at angle 3 and angle 1, those are going to have the same measure. Angle 1 and angle 3 are going to be equal to each other for the same reason. It's because they're vertical angles. Back to back is a really nice sort of way for us to say, that's how we'll find vertical angles, but you could also be more formal and say they share a vertex, but nothing else. They don't share any sides. Any questions about any of that up to now? We've gone through points, lines, and planes. We mentioned collinear and non-collinear. We did lines, line segments, and rays. Parallel lines, perpendicular lines, concurrent lines, skew lines, naming angles using vertices, along with points that are on the rays that help to make the angle, right angles, acute angles, obtuse angles, straight angles, adjacent angles, complementary and supplementary angles, and vertical angles. A whole lot of terms and definitions that I want to make sure you're comfortable with. If you have any questions about any of those, let me know before we look at a couple of problems that we actually do get to solve. Okay, outstanding. Let's see if we can find some angle measures. And it's a device that our book uses that I think is excellent. What angle is made when it's 9 o'clock? And so if it's 9 o'clock, we sort of have to imagine our clock here, or we don't have to imagine, we can actually just draw one. And then I'm going to put the hands of my clock on here, and It's 9 o'clock. What angle is made? What we're talking about, I guess my hour hand should be shorter than my minute hand. Let me fix that up. There we go. So it's 9 o'clock, and the question is, oops, I gave it away, dummy. What I want to know is, what is the measure of this angle right here? Well, I gave it away. I drew it in there already. And you probably already know that that's a 90-degree angle because it's these two lines are perpendicular. My hour hand and my minute hand are perpendicular. And so a 90-degree angle is when it's 9 o'clock. I do want you to think about that for a minute, though. The idea that that's 1, 2, 3 spots from 12 o'clock, and we had 90 degrees. With that in mind, I want to let you try one. What angle is made when it's 10 o'clock? I'll set up a poll for this and let you try it. And I kind of think it helps to go ahead and draw a clock, but you don't necessarily have to. But the idea is what angle is made when it's 10 o'clock. One thing I should say is, and you can see this from the poll options, what we're talking about is the acute angle. We're not talking about the big giant angle that would go all the way around. We're talking about the angle that's made between the two hands, the acute angle that's in between the two hands. I don't necessarily think these clock questions are easy. You kind of have to think about them a little bit. Once we talk about them in class today, I think you'll be completely comfortable. But at first glance, I don't think they're immediately obvious. I do like these very much, though. So it's something that you should expect to see in homework, on a quiz, possibly on an exam. I don't remember if that's something I have in my notes for the exam or not off the top of my head, but I definitely want to make sure you know how to do them. So let's see if we can get to that point. Let's go another 25 seconds on this, and then we'll talk about it. All right, let's see how we did. Okay, kind of split on this one, and not everybody's in there. So we'll be patient and careful as we go through this one. All right, so the first thing I'm going to want to do in approaching this, me personally, you don't have to, but the first thing that I'm going to do is go ahead and draw a clock, because that's going to help me out. It's going to get me to where I can answer the question. So I'm going to draw myself a clock, and I'll have 12, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. It doesn't have to be perfect. I don't expect you to get out a protractor and measure. That's not what's happening here. We're going to calculate it. And so I put my hands on here, and it's 10 o'clock. And what I want to know is, what is the measure of this angle here? When you're asked for an angle measure in a question like this, I just want to sort of reiterate, it's not talking about this angle all the way around the outside. We're talking about the acute angle that's just the one right here. Now, a minute ago when we did 9 o'clock, it was pretty obvious to us that, well, when I did 9 o'clock, that was 90 degrees. And so that means if I go 1, 2, 3 spots from 12, that's 90 degrees. What that means is each one of these spots, well, it's 30 degrees to get to 11, it's 30 degrees to get to 10, and 30 more degrees to get to 9. Because, the clock is symmetric. Each one of these is the same distance from each other. And so what that means then is if it's 10 o'clock, then that means, well, 30 degrees over here would put me at 11. 30 more degrees moves me to where it's 10. So this angle right here has to be 60 degrees. And there's nothing more to it than that. We're not guessing. What we're doing really is we're taking the 360 degrees that's all the way around that circle, and we're dividing that by 12 to find that each time I move one number, I'm moving 30 degrees. And so if I have to be 2 numbers away, that means it's a 60-degree angle. Let me know if you have any questions on that before I have you try one more that's a little harder. Okay. What angle is made when it's 6:30? I'll set up a poll for this and let you try it. This one's a little harder. I will tell you to be careful. And if you don't know, can't tell is okay for an answer. It's totally fine. It's all right. A lot of times we don't like to admit when we don't know things, but it's okay. That's, if you already knew everything, then you could test your way right out of the class. You wouldn't have to take it at all. But that's not the case for us very often. It's okay to not know things. There's tons of things I don't know, and I admit it all the time. Let's go another 30 seconds on this one, and then we'll talk through this one together. I do think it's a challenging question. More challenging than it appears on the surface. All right, let's go ahead and take a look at this one then. We got some there at the last minute. That's excellent. Okay, so we've got some agreement here, but not universal. So let's go make sure that we're all seeing this one the same way. Just like last time, the first thing I'll do here is draw myself a clock so that I have something to work with. And so we'll put that on there. And then I need the hands of my clock, and it's 6:30. And at first glance, when I go, well, then 6:30, so it's 0. But wait a minute, that hour hand, it doesn't wait until 7 o'clock and then jump all the way from 6 bing, to 7 when it gets to 7 o'clock. That hour hand is moving the whole time. And so what that means is when the minute hand is down here at 30, that means that the hour hand is halfway to the 7. And since it's halfway to the 7, well, let's see, all the way to the 7 would be 30 degrees. Since it's halfway over to the 7, that angle is 15 degrees. Borderline trick question, but not really, especially because now we've talked about it. So it's out there in the open. If it's something 30, then the hour hand is halfway to the next number. So keep that in mind as you do problems like this one, where, if it's something o'clock, then you're looking at this idea where it's 30 degrees between each number. That's how you'd find your angle. When it's something 30, now it's half of the way between the numbers. The hour hand is halfway between the numbers. So keep that in mind when you go to figure out the angle, because that's going to play